Physics Part 110. Returning to the combination of three gas laws and using number n of moles of the gas, we have PV is equal to nRT, or putting in a new constant of proportionality R. R is called the molar gas constant, sometimes the universal gas constant, because it has the same value for all gases. It has the value of 8.3 joule kilogram per mole. Sometimes the equation PV is equal to nRT is expressed in the form of PVM is equal to RT, where the molar volume Vm is the volume occupied by 1 mole of the gas. Another version is PV is equal to nKT, where n is the number of molecules in the gas and the K is constant, called the Boltzmann constant. It has the value of 1.38 into 10 power raised to minus 23 JK1. The molar gas constant and the Boltzmann constant K are connected through the Avogadro constant. R is equal to Kna. Strictly speaking, the laws of Boyle, the laws of Charles, the laws of Gay-Lussac are not really laws, as their validity is restricted. They are accurate for the real gases only if the pressure of the sample is not too great, and if the gas is well above the liquefaction temperature. But they can be used to define an ideal gas. An ideal gas is one which obeys the equation of the state PV is equal to nRT at all pressures, volumes and temperatures. We have already used the ideal gas equation to introduce the idea of thermodynamic temperature. For approximate calculations, the ideal gas equation can be used with real gases. There are few examples. Number one, find the volume occupied by 1 mole of air at standard temperature, pressure 273 K, and 1.01 into 10 power raised to 5 PA. Taking R as 8.3 JK minus 1, mole minus 1 for air. Since PV is equal to nRT, V is equal to nRT over P, substituting the values n is equal to 1 mole, we get an answer of 2.24 into 10 power raised to minus 2 meter cubic. Find the number of molecules per cubic meter of air at standard temperature and pressure. We have just shown that the volume occupied by 1 mole of air at standard temperature and pressure is 2.24 into 10 power raised to minus 2 meter cubic. 1 mole of air contains Na molecules, where Na is the Avogadro constant. Thus, the number of molecules per cubic meter of air is 6.0 into 10 power raised to 23 divided by 2.24 into 10 power raised to minus 2. The answer is 2.69 into 10 power raised to 25 meter cubic. Note, it is useful to remember that these two quantities, the molar volume of a gas and the number density of molecules in it, they give an idea of the relatively small volume occupied by the mole of a gas at standard temperature and pressure. A cube of side about 28 cm, an enormous number of molecules in every cubic meter of a gas under these conditions. Number 3. We've got third example, and I find it very manageable to provide this example in my next video.